Introduction to QoS. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Quality of service. QoS is a critical concept in network management that ensures important traffic gets priority over less critical traffic. In this presentation, we will explore how to implement QoS using two powerful Linux tools: TC, traffic control, and iptables. These tools work together to shape, prioritize, and manage network traffic at the kernel level, helping maintain performance and reliability in networks with limited bandwidth or high demand. What is QoS? QoS stands for Quality of Service. It is a set of techniques and mechanisms that manage network resources to ensure certain traffic types get preferential treatment. In modern networks, we often have multiple applications competing for bandwidth, for example, video streaming, voice over IP calls, file transfers, and web browsing. Without QoS, these applications may compete unfairly for bandwidth, resulting in poor performance for time-sensitive traffic like voice or video conferencing. QoS allows network administrators to prioritize critical traffic by applying policies that control how packets are queued, scheduled, and transmitted over the network. Why use TC? TC, or traffic control, is a powerful Linux utility that provides advanced packet scheduling, queuing disciplines, and traffic shaping capabilities. It's part of the Linux kernel's networking stack and gives fine-grained control over how network packets are handled at the interface level. With TC, you can implement various queuing disciplines like FIFO, CBQ, HTB, and SFQ. These queuing disciplines allow you to create classes of traffic with different priorities, bandwidth limits, and scheduling policies. Basic TC concepts. The fundamental building blocks of TC are queuing disciplines, classes, and filters. A queue disk is a queuing discipline that determines how packets are queued for transmission. It's the foundation of traffic control. Classes organize traffic into different categories based on priority or service level, each with its own parameters. Filters direct traffic to specific classes based on matching criteria such as source/destination IP addresses, ports, or protocols. Together, these components create a hierarchical structure where packets are classified and shaped according to defined policies. Understanding HTB. HTB, Hierarchical Token Bucket, is one of the most popular queuing disciplines used in QoS implementations. It provides a hierarchical structure where bandwidth is allocated at different levels, with parent classes controlling child classes. HTB uses token buckets to regulate traffic. Packets are only allowed to pass if there are sufficient tokens available in the bucket. This allows for precise bandwidth control and ensures that high-priority traffic gets its guaranteed bandwidth while low-priority traffic is limited or shaped. HTB configuration example. Let's look at a practical example of configuring HTB on an interface. First, we initialize the root queue disk with HTB. The command sets up a basic HTB structure on the ETH0 interface with a default class that handles all unclassified traffic. This configuration creates a hierarchy where bandwidth is allocated based on priority, ensuring critical services maintain performance. Creating classes. After setting up the root queuing discipline, we create classes for different traffic priorities. The first class, 1-to-1, is for high-priority traffic with guaranteed bandwidth of 50 megabits per second and a maximum rate of 100 megabits per second. The second class, 1:2, handles normal traffic with 30 megabits per second guaranteed bandwidth and 60 megabits per second maximum. Finally, the default class 1:3 manages best effort traffic with only 10 megabits per second guaranteed bandwidth. This structure ensures that critical applications get their required bandwidth while limiting less important traffic to prevent network congestion. Filtering traffic. Now we need to direct traffic into the appropriate classes using filters. Filters match packets based on criteria and send them to specific classes. In this example, we use protocol matching to direct SSH traffic, port 22, to the high priority class. We also filter HTTP traffic, port 80, to the normal priority class, ensuring web browsing gets appropriate bandwidth. These filters are crucial for implementing QoS policies. They determine how different types of traffic are treated based on their importance. iptables integration. iptables works alongside TC to create a comprehensive QoS solution by marking packets that need special treatment. Packets can be marked with specific values using iptables rules, which can then be used by TC to direct them to appropriate classes. This integration allows for more sophisticated policies where traffic classification is done at the network layer rather than just transport layer. By combining these tools, we can implement complex QoS rules that adapt to real-time network conditions and application requirements. Packet marking with iptables. We use iptables to mark packets with specific values that TC can recognize and act upon. The first rule marks packets from a specific source network 192.168.1.0/24 with a value of 0x10, which corresponds to high priority. Another rule marks packets destined for a specific destination port 5000 as important traffic. These markings are stored in the packet's TOS field or through iptables mark target, making them available to TC for classification. Applying markings to TC. Once packets are marked by iptables, we can use TC filters to direct them to appropriate classes. The filter uses the FW, or firewall, classifier with the mark value 0x10 to match marked packets and direct them to class 1:1. This creates a seamless flow from iptables packet marking to TC traffic classification, providing end-to-end QoS control. By using this approach, we can implement complex policies that combine network layer filtering with traffic shaping. Advanced TC features. TC supports many advanced features beyond basic queuing disciplines. For instance, you can use rate limiting to control burst sizes. It also supports traffic policing with different algorithms for handling excess packets, dropping, marking, or shaping them. Additionally, TC allows for complex hierarchical structures where classes can be nested to create fine-grained control over network resources. These features make TC a powerful tool for implementing sophisticated QoS policies in enterprise environments. Real-world example. Let's consider a real-world scenario where we have a small business network with various traffic types. We want to ensure VoIP calls get priority over file transfers, and web browsing doesn't interfere with critical business applications. Using TC and iptables together, we can classify voice traffic, typically UDP port 5060, as high priority and limit bandwidth for large downloads. This ensures consistent performance for mission-critical services while still allowing other traffic to use available bandwidth efficiently. Monitoring QoS. Once QoS policies are implemented, monitoring is crucial to ensure they're working as intended. You can use TC's built-in statistics to monitor packet counts, dropped packets, and bandwidth usage per class. iptables also provides logging capabilities that help identify which traffic is being marked and how it's being handled. Regular monitoring allows you to fine-tune QoS policies based on actual network usage patterns. Performance considerations. Implementing QoS with TC and iptables has performance implications that need to be considered. Each packet processing step adds overhead, so it is important to optimize rules for efficiency. Too many filters can cause packet delays, while overly complex hierarchies might not provide proportional benefits. Testing under realistic conditions is essential before deploying QoS policies in production environments. Common issues and solutions. One common issue is misconfigured filters that do not properly classify traffic. This can result in all traffic going to the default class, defeating the purpose of QoS. Another issue is incorrect bandwidth allocation. Specifically, setting too low values for high-priority classes may cause service degradation. Always validate your configurations and monitor performance after implementation. Best practices. Start with a simple configuration and gradually add complexity. Always test QoS policies in a controlled environment before production deployment. Use appropriate queuing disciplines for your use case. For example, HTB is good for hierarchical control, while SFQ works well for fair sharing. Document all rules and configurations for easier maintenance and troubleshooting. Use cases. QoS with TC and IP tables is particularly useful in various scenarios. In networks with limited bandwidth, critical services require guaranteed performance. Enterprise environments where VoIP, video conferencing, and business applications must have priority over general internet traffic. There are data centers that need to manage bandwidth allocation between different tenants or services. Any environment where predictable network performance is more important than maximizing throughput. Summary. We've explored how to implement QoS using TC and IP tables, covering essential concepts from basic queuing disciplines to advanced configurations. TC provides traffic shaping capabilities using queuing disciplines, such as HTB, for hierarchical bandwidth allocation. IP tables handles packet classification through marking, which TC then uses for directing traffic to appropriate classes. This combination gives you precise control over network resources, ensuring critical applications receive priority treatment while maintaining efficient bandwidth usage. Conclusion. Thank you for your attendance. Please consider subscribing to the channel. QoS implementation with TC and IP tables is a powerful approach for managing network resources effectively. With careful planning, proper testing, and ongoing monitoring, these tools can significantly improve network performance and user experience. Remember to always validate your QoS policies and adjust them based on actual network behavior rather than theoretical assumptions.